Welcome back to Sky Creative Channel. From floating wind turbines in the North Sea to mega airports that redefine human ambition, join us as we explore the engineering marvels that transformed our world. These aren't just construction projects. They're testaments to human ingenuity and the timeless craft of building great things. Back in the 1970s, when the oil crisis hit America hard, engineers around the world started dreaming about harnessing wind power from the ocean. But here's the thing. Nobody quite figured out how to do it in deep water until Spanish engineering firm Esteco came along with something revolutionary. Now let me tell you about Elisa. And no, it's not somebody's grandmother, though the technology is just as reliable. Elisa stands for Esteco's Innovative Platform Design, and it's built on what engineers call a GBS, or gravity-based structure foundation. Think of it like an iceberg. Most of the action happens below the waterline. The foundation uses a self-floating concrete structure that's absolutely massive, weighing thousands of tons. Yet it floats as gracefully as a cork in a bathtub. The real genius here is in the telescopic tower design. Picture those old radio antennas that slide up and down. That's essentially what they built, but on a scale that would make your jaw drop. The tower sections are constructed onshore using advanced concrete casting techniques, with each segment precisely engineered to fit inside the next, like a giant set of Russian dolls. This telescopic design solves a problem that plagued offshore construction for decades. How do you build something tall without needing impossibly expensive crane vessels? The construction process is something to behold. First, they fabricate the base platform using slip-forming techniques. That's a method where concrete is poured continuously as the formwork slowly moves upward. The concrete mix itself is special, containing additives that make it resistant to saltwater corrosion and able to cure properly even in marine environments. Once the base is ready, they bring in floating cranes. These aren't your grandfather's construction cranes. We're talking about specialized vessels with dynamic positioning systems that use GPS and thrusters to hold position within inches, even in rough seas. These cranes lift and position the tower sections, which are then locked together using post-tensioning cables. These cables, made from high-strength steel tendons, are threaded through ducts in the concrete and then tensioned to over 200 tons of force, binding everything together stronger than any weld could. The ballasting system is pure engineering poetry. Large compartments in the base can be filled with seawater or pumped dry to adjust the platform's stability and draft. During installation, they carefully control the ballast to float the structure to the installation site, then flood specific compartments to lower it into position. What really sets this apart from older offshore platforms is the mooring system. Instead of being permanently anchored to the seabed like old oil rigs, the Elisa platform uses a catenary mooring system with 3 or 4 massive anchor points spread in a circle around the turbine. Each mooring line is a combination of heavy chain and synthetic rope, carefully calculated to allow the platform to move with waves and wind without drifting away. The turbine itself sits atop this engineering marvel, a 5-megawatt beast with blades spanning over 120 meters. Installing it requires perfect weather windows and precision that would make a watchmaker proud. The nacelle, that's the housing containing the generator and gearbox, weighs about 70 tons and has to be lifted and secured in conditions where even a slight miscalculation could spell disaster. This prototype in the Canaries proved something important. You could build offshore wind farms in waters too deep for traditional fixed foundations. It opened up vast areas of ocean to renewable energy development, especially along coastlines, where the continental shelf drops off quickly. Let me take you back to 2017, to a stretch of the North Sea, about 15 miles off the Scottish coast, where Norwegian energy giant Equinor did something nobody had done before at commercial scale. They built Hywind Scotland, the world's first floating wind farm, and in doing so, they rewrote the rulebook on offshore energy generation. The construction process started in shipyards in Norway and Spain, where these enormous cylinders were fabricated from steel plate. We're talking about premium-grade structural steel, the same stuff used in ship hulls, but thicker. The welding alone took months, with certified welders working in climate-controlled conditions to ensure every joint met stringent maritime standards. Each section was ultrasonically tested. Sound waves can detect microscopic flaws that might become catastrophic failures years down the line. The assembly process was choreographed like a ballet. First, they'd float the spar structure to a sheltered deepwater port. Then came the delicate operation of mounting the tower and turbine. They used specialized heavy-lift vessels, ships designed specifically for offshore wind installation, equipped with jack-up legs that let them become stable platforms in the middle of the ocean. The Saipem 7000, one of the world's largest crane vessels, handled some of the lifts, its twin cranes capable of hoisting 7,000 tons in tandem. Each turbine is a 6-megawatt Siemens Gamesa model, with blades measuring 75 meters long. These aren't your daddy's windmill blades. They're aerospace-grade carbon fiber and fiberglass composites, manufactured in precision molds with tolerances measured in millimeters. The blade design incorporates decades of aerodynamic research, with twisted profiles and varying chord lengths optimized to capture maximum energy across different wind speeds. The mooring system for Hywind Scotland represents some seriously impressive engineering. Each turbine is held in position by 3 suction anchor points on the seafloor, about 100 meters down. These aren't traditional anchors. They're massive steel skirts, 20 feet in diameter, that are pushed into the seabed and then pumped to create suction. It's like sticking a giant suction cup to the ocean floor, and the holding power is phenomenal. From each anchor, heavy mooring chains extend up to the spar buoy, allowing the turbine to move within a carefully calculated radius. Here's something fascinating. The turbines are designed to weather vane, meaning they naturally rotate to face into the wind, like a weather vane on a barn roof. But unlike fixed turbines that use complex yaw drives with enormous electric motors to turn the nacelle, these floating turbines let the whole structure rotate around its mooring point. The mooring lines are configured to allow this rotation while preventing the lines from tangling, a clever piece of marine engineering that old-time sailors would appreciate. The tow-out to the installation site was an operation worthy of a naval convoy. Each completed turbine, fully assembled and floating upright, was towed by tugboats making perhaps 5 knots, slower than walking pace, on a journey that took several days. During the tow, engineers monitored ballast levels constantly, adjusting water in the internal compartments to maintain proper trim. One miscalculation could cause listing or even capsize, turning months of work into an expensive artificial reef. Installation required weather windows, periods of at least 48 hours with seas below 6 feet and winds under 25 knots. In the North Sea, such windows are precious and unpredictable. When conditions aligned, specialized installation vessels would connect the pre-laid mooring lines to each turbine spar, carefully managing tensions to ensure even loading. Once all 3 moorings were secured, they'd fine-tune the ballast to achieve the perfect draft depth. The electrical connection system deserves its own mention. Each turbine has a dynamic cable that hangs in a catenary curve down to the seabed, then runs along the ocean floor to a subsea hub. These cables need to flex with the turbine's movements without fatiguing. It's similar to the challenge of designing cables for suspension bridges, but underwater and with electrical insulation that must never fail. The cables use cross-linked polyethylene insulation, protected by multiple layers of armor wire and outer sheaths. Since going operational, Hywind Scotland has outperformed all expectations, achieving capacity factors above 50%, meaning it generates at more than half its maximum capacity on average. That's remarkable for wind power. The project proved that floating turbines could not only survive, but thrive in harsh open ocean conditions, generating clean electricity that powers thousands of Scottish homes. For those of us who remember when offshore meant oil rigs and pollution, seeing these giants spin silently in the wind represents real progress toward a cleaner future. Let me tell you about one of the most ambitious construction projects of the 21st century, Istanbul Airport. A project so massive, it makes most American airports look like regional commuter hubs. When it opened in 2018, this wasn't just an airport, it was a statement, a mega hub designed to handle 200 million passengers annually when fully completed. To put that in perspective, that's like every person in California, Texas, and Florida flying through the same airport twice a year. The story starts with site selection and preparation, and this is where modern construction technology really shines. The chosen location in the Arnavutkoi district presented serious challenges. It was mostly forested land with uneven terrain and questionable soil stability. Before a single shovel of dirt could be moved, geotechnical engineers conducted extensive soil testing using truck-mounted drill rigs that can bore hundreds of feet down, extracting core samples every few inches. These samples went to laboratories where they tested soil-bearing capacity, water content, and shear strength. The data revealed areas where the natural soil simply couldn't support massive terminal buildings, requiring extensive ground improvement. The ground improvement work alone was extraordinary. They used a technique called dynamic compaction, where enormous weights, we're talking 20 to 40 tons, are dropped repeatedly from heights of 60 to 100 feet. The impact compacts loose soil, increasing its density and load-bearing capacity. In some areas, they installed stone columns using vibroflotation equipment. These machines vibrate a probe deep into the ground while simultaneously pumping in crushed stone, creating reinforced columns throughout the soil like rebar and concrete. Over 200,000 of these columns were installed across the site. Clearing and grubbing operations required a fleet of heavy equipment that would make any construction veteran's heart race. Caterpillar D11 bulldozers. These are the biggest dozers made, weighing 230,000 pounds with 850 horsepower engines, worked alongside Komatsu PC8000 excavators. The PC8000 is a genuine monster, standing 4 stories tall with a bucket that can scoop 42 cubic meters in one bite. These machines operated around the clock in coordinated waves, with GPS guidance systems ensuring they cut to precise grades. The earth-moving operation was choreographed using sophisticated fleet management software. Every dump truck, and they had over 500 Volvo and Caterpillar articulated haulers on site, was tracked in real time via GPS. The system optimized routes, automatically dispatching trucks to loading points and directing them to fill areas, minimizing idle time and fuel consumption. It's like having air traffic control for dirt haulers. At peak construction, they were moving 4 million cubic meters of earth per month. For the runway construction, they employed techniques refined over decades of airfield building. The foundation starts with compacted subgrade, tested every few hundred feet to ensure uniform density. Then comes a layer of aggregate base course, crushed stone, carefully sized and graded, spread by massive spreaders and compacted by vibratory rollers weighing 25 tons. These rollers use eccentric weights spinning at high speed to send vibrations deep into the stone, packing it incredibly tight. Engineers test compaction using nuclear density gauges, devices that measure how tightly packed the soil is by bouncing radiation through it. The concrete paving for runways and taxiways used slip-form pavers, magnificent machines that changed runway construction forever. If you remember watching the interstate highways being built, you've seen slip-form pavers in action. These machines straddle the paving area, receiving fresh concrete from a fleet of mixer trucks. As the paver slowly moves forward, maybe 5 feet per minute, it continuously places, spreads, compacts, and finishes the concrete in one smooth operation, leaving behind perfectly profiled pavement. Istanbul Airport's main runways are 60 meters wide, requiring specialized high-production pavers working in tandem. The concrete mix for airport pavement is specially designed. It needs to withstand not just the weight of aircraft, a fully loaded Airbus, A380 weighs 1.2 million pounds, but also the heat from jet engines and the constant pounding of landing gear. They used high-strength concrete with a 28-day compressive strength of 500 psi, reinforced with steel mesh and containing special additives to reduce shrinkage and increase durability. The concrete includes fly ash, a byproduct of coal power plants that actually makes concrete stronger and more resistant to chemical attack. Temperature control during concrete placement was critical. Concrete generates heat as it cures, and in large pores, this heat can cause cracking. They embedded thermocouples throughout the slabs to monitor internal temperatures, and in hot weather, they used chilled water in the mix and covered fresh concrete with insulating blankets to slow the curing process and reduce thermal stress. The terminal building construction showcased modern steel erection techniques on a grand scale. The main terminal spans 1.4 million square meters. That's about 350 acres under one roof. The structural steel frame required 135,000 tons of steel, all fabricated to precise specifications in specialized factories. Each steel member arrived on site with computer-generated erection drawings showing exactly where it fit in the three-dimensional puzzle. Mobile cranes handled most of the steel erection, massive machines like the Liebherr LR 11350, a crawler crane that can lift 350 tons. These cranes use lattice booms extending over 400 feet into the air, assembled section by section on site. The crane's computer system continuously calculates load moment and automatically prevents operations that would exceed the crane's capacity. Ironworkers. The brave folks who connect the steel worked hundreds of feet in the air, bolting and welding connections following strict procedures. The roof structure deserves special attention. It uses a digrid system, diagonal structural members forming a triangulated pattern that's both incredibly strong and aesthetically striking. This design, inspired by traditional Turkish patterns, spans vast distances without internal columns, creating wide-open interior spaces. The steel digrid supports a roof assembly including insulation, waterproofing membranes, and a finished ceiling, all suspended from the structural frame using hanger systems. Curtain wall installation. The glass and metal exterior envelope employed automated systems that old-time glaziers would find astonishing. Prefabricated wall units, each containing multiple panes of insulated glass and aluminum frames, arrived on specialized trucks. Spider cranes, compact cranes that can operate inside buildings, lifted these units into position, where installation crews secured them to embed plates cast into the structure. Each connection point includes thermal brakes to prevent heat transfer and gaskets to seal against air and water infiltration. The mechanical, electrical, and plumbing systems in a facility this large are mind-boggling in complexity. Consider the HVAC system. It needs to maintain comfortable temperatures and air quality for tens of thousands of people simultaneously in a building with vast glass walls and numerous heat sources. They installed air handling units the size of small houses, each capable of moving hundreds of thousands of cubic feet of air per minute. Ductwork fabrication and installation required sheet metal workers to create miles of custom ducts, all following sophisticated CFD, computational fluid dynamics models that optimized airflow. The chilled water system for air conditioning uses massive centrifugal chillers. Each unit is the size of a semi-truck trailer and can produce thousands of tons of cooling capacity. These chillers circulate chilled water through underground piping networks, spanning the entire site, with backup systems ensuring uninterrupted operation even during maintenance. The boiler plant for heating uses high-efficiency condensing boilers, orchestrated by building management systems that continuously optimize energy consumption. Electrical infrastructure rivals that of a small city. The airport has multiple substations receiving power at 154 kilovolts from the Turkish national grid, stepping it down through massive transformers to usable voltages. Emergency power comes from diesel generators. They installed 26 units totaling 76 megawatts of backup capacity. These generators can carry the full critical load indefinitely, ensuring life safety systems, navigation aids, and essential facilities never lose power. The baggage handling system is a marvel of automated logistics. Conveyor belts totaling over 42 kilometers in length connect check-in areas to sorting facilities to aircraft loading positions. High-speed sorters use laser scanners and RFID readers to identify bags, routing them through the system at speeds up to 10 meters per second. Automated tug vehicles carry baggage containers from the sorting facility to aircraft, following magnetic tracks embedded in the pavement. Fire protection systems were designed to the most stringent aviation standards. The terminal has over 20,000 sprinkler heads, supplied by fire pumps capable of flowing thousands of gallons per minute. Specialized foam systems protect aircraft parking positions and fuel facilities, using foam concentrate that smothers jet fuel fires by blocking oxygen. Early warning smoke detection uses air sampling systems that continuously draw air from throughout the building, analyzing it for combustion byproducts. Throughout construction, they employed Building Information Modeling (BIM) three-dimensional digital models containing every component of the project. Architects, engineers, and contractors worked within this shared model, identifying conflicts before construction began. When a pipe route conflicted with a structural beam, the computer found it, not workers on site facing costly delays. This technology, combined with rigorous project management, enabled them to complete this massive project in just 42 months. The final result is a facility that handles aircraft movements with incredible efficiency. 6 runways, each 750 meters long and equipped with Category 3 instrument landing systems, can accommodate simultaneous operations in nearly any weather. The air traffic control tower, standing 95 meters tall, gives controllers a commanding view of the entire airfield, equipped with surface movement radar that tracks every aircraft and vehicle. Istanbul Airport represents the culmination of a century of aviation infrastructure development, incorporating lessons learned from every major airport built before it, enhanced by 21st century technology and Turkish determination to create a world-class gateway. Let me share a story about a bridge project that brought together German precision and Australian know-how in an unlikely location, Vietnam. The Phu My bridge in Saigon was built by BBBH, a joint venture between Germany's Bilfinger Berger Civil and Australia's Balderstone Hornibrook, two companies with deep roots in heavy construction. Construction began with foundation work in the river, always challenging and dangerous. They used cofferdams, temporary watertight enclosures pumped dry so workers can excavate and build in what's normally underwater. The cofferdams were constructed from interlocking sheet pile, steel sheets with edges that connect together like a giant jigsaw puzzle. Vibratory hammers drove these sheets deep into the riverbed, their rapid vibration reducing soil resistance and allowing the sheets to penetrate. Once the cofferdam was complete and pumped dry, workers excavated down to bedrock, encountering the soft clay soils typical of river deltas. Foundation piles were driven using hydraulic impact hammers mounted on cranes operating from barges. These hammers deliver tremendous blows, up to 500 tons of impact force, driving steel pipe piles through soft soil into underlying bedrock. Each pile was instrumented during driving, with sensors measuring stress waves traveling through the steel. The concrete for the tower piers used self-climbing formwork systems, German engineering at its finest. These systems, developed by companies like Doka and Perry, consist of modular steel forms that climb the structure as it rises. Hydraulic jacks push the forms upward on steel rails, allowing crews to work at safe heights with platforms and safety barriers always in place. The cable stay towers themselves are dramatic concrete structures rising 120 meters above the water. Constructing them required precision concrete work. The towers are hollow box sections with walls varying from 60 to 80 centimeters thick, cast in lifts of 4 to 5 meters. Each concrete pour required careful mix design, using local cement, but supplemented with imported additives to achieve the required strength and durability. Concrete pumps push the mix through delivery pipes to the forms, sometimes lifting it over 100 meters vertically, a task requiring pumps with enormous pressure capacity. The stay cables are engineering marvels themselves. Each cable consists of hundreds of individual steel strands, each strand made of 7 high-strength steel wires twisted together. These strands are parallel, protected by polyethylene sheathing and tensioned to incredible forces. Some cables carry loads over 2,000 tons. The cables were manufactured in Europe, shipped to Vietnam, and installed by specialized crews using hydraulic jacks to pull each strand to precise tension. The bridge deck was built using balanced cantilever construction, a method perfectly suited to cable-stayed bridges. Starting from each tower, construction crews worked outward in both directions simultaneously, keeping the towers in balance. Traveling formwork, carried on the last completed section, supported the next segment. This system, controlled by sophisticated surveying equipment, ensured the bridge deck met in the middle with millimeter accuracy. This project showcased how international construction expertise can tackle challenging projects in developing nations, bringing advanced techniques and equipment to create infrastructure that serves millions. The Phu My Bridge stands today as a testament to German-Australian engineering excellence applied with Vietnamese determination.